Compute is where the money is in AML, and it's where the AI-300 exam focuses the most D1.1 questions. Let's get the two primary compute types absolutely clear: instances and clusters. A compute instance is a single managed virtual machine in your workspace. It's fully managed. Microsoft handles the OS patches, the driver updates, and the network integration. Data scientists use compute instances for interactive work, running Jupyter notebooks, exploring data, prototyping training code. Key instance behaviors to know for the exam: they stay running until you stop them, so they cost money even when idle. Unlike clusters which scale to zero, they can be assigned to a specific user, so no one else uses them. And they come with the AML Python SDK and CLI pre-installed. A compute cluster is an auto-scaling pool of virtual machines. You set a minimum node count, typically 0 for cost savings, and a maximum node count. When a training job is submitted, the cluster scales up to the requested number of nodes, runs the job, and then scales back down to 0 after the idle timeout. The idle timeout, idle_time_before_scale_down, is set in seconds. If you set it to 1800 seconds, nodes stay warm for 30 minutes after the last job before scaling to 0. Set it too high and you pay for idle nodes. Set it too low and cold start times slow your team's iteration. VM size selection is a frequent scenario question. Standard_DS3_V2 is a general purpose CPU VM. Fine for data prep, light training. And inference, standard_NC6S_V3 or NDA100V4 are GPU VMs, required for deep learning training. The exam will give you a scenario like data scientists are training a PyTorch image classifier that takes 8 hours on CPU and ask you to pick the right solution. The answer is a GPU compute cluster. Spot instances, called low priority nodes in AML, are Azure Spot VMs attached to a cluster. They cost 60 to 90% less than regular VMs, but Azure can evict them at any time when demand spikes. For training jobs that use spot nodes, checkpointing is mandatory. If a node gets evicted, the job must resume from its last checkpoint, rather than starting over. This is an exam topic. Spot instances for cost optimization require checkpoint-enabled training code. Beyond instances and clusters, AML offers two additional compute options that appear on the exam: serverless compute and attached compute. They solve different problems, and you need to know when each one is the right answer. Serverless compute is the newest option and the simplest to operate. Instead of creating a cluster and managing its lifecycle, you submit a job with a serverless compute specification. Compute serverless in your job YAML. And AML provisions the required VMs automatically, runs the job, and terminates the VMs when the job completes. No idle cluster, no scale down timeout to manage, no quota to pre-allocate. You just pay for the exact duration of the job. Serverless compute is ideal for teams with infrequent training jobs that don't want to maintain a cluster, or for jobs with highly variable resource needs. The trade-off is cold start time. Serverless provisioning takes a few minutes longer than a pre-warmed cluster. When would you not use serverless? When job startup latency matters. If your team submits dozens of short training jobs per day and cold start time becomes a significant fraction of total job time, a pre-provisioned cluster is faster. Serverless is best for longer jobs where a 1 to 2 minute provisioning delay is negligible. Attached compute works differently. Instead of AML managing the compute, you bring existing infrastructure into the AML workspace. Two types matter for the exam. First, attached to AKS. If you have a production Kubernetes cluster already running for inference workloads, you can attach it to AML and deploy model endpoints onto it instead of using AML's managed online endpoints. This is useful when you need more control over the Kubernetes configuration or when you're deploying into an existing Kubernetes-based platform. Second, attached Databricks. If your data engineering team already runs Apache Spark workloads on Azure Databricks, you can attach the Databricks workspace to AML and submit training jobs that run on Spark. This pattern is common for organizations with large-scale data prep pipelines that feed ML training. Exam tip. Attached compute is always the answer when a scenario says the team already has A. That's managed separately. How do you run AML jobs on it? Azure ML Compute is the largest cost driver in any AML environment, and managing that cost is explicitly part of the MLOps engineer's job description. The exam includes cost optimization scenarios. Let's cover the 5 practices that consistently show up. First and most impactful, set min_instances. 0 on every compute cluster. With 0 minimum nodes, the cluster scales completely to 0 when no jobs are running and you pay nothing. The counterintuitive trap is setting min_instances, one thinking you're reducing job startup time. That one node runs 24/7 and accumulates cost even when nobody is training. Only set a non-zero minimum when you've measured and proven that cold start time is a genuine productivity bottleneck, and the cost of idle nodes is less than the cost of waiting. Second, low priority nodes for fault-tolerant workloads. If your training job supports checkpointing and can survive a mid-run node eviction, use low priority nodes. Azure can evict them but gives you at least 30 seconds of warning, which is enough to write a checkpoint. The cost savings are substantial, 60 to 90% cheaper than dedicated nodes for the same VM size. The exam frames this as, the team wants to minimize cost for overnight training runs that can tolerate occasional restarts. What should they configure? Low priority nodes with checkpointing. Third, auto shutdown for compute instances. A developer who leaves a compute instance running over a long weekend generates surprising charges. Configure the auto shutdown schedule on every instance. Typically 8 hours of idle time before shutdown. Users can override it for specific sessions, but the default should shut down idle instances. Fourth, reserved instances. If you have a workload that runs predictably and continuously, say a daily batch inference job or a model training job that runs every night, Azure reserved instances can reduce that cost by up to 70% versus pay-as-you-go. You commit to a 1-year or 3-year reservation for a specific VM family in a specific region. This is a FinOps level optimization, and the exam tests your awareness of it as a production tool. Fifth, workspace level quota caps. Set a maximum core limit per workspace so a misconfigured pipeline that accidentally launches 1,000 parallel jobs hits the cap rather than generating a massive bill. This is cost governance, and it's cheap insurance. Lab 2 puts compute configuration into practice. You're using the workspace you built in Lab 1 and adding compute to it, specifically a compute instance for your dev work and an auto-scaling compute cluster for training jobs. Both are created via the Azure CLI, and you'll configure the cluster with low priority nodes and a 10-minute idle scale-down timeout. After creating both, you'll verify the configuration in Azure ML Studio and then submit a simple test job to watch the cluster scale from 0 to 1 node and back. The test job is a 1-line Python script. The point isn't the code, it's watching the cluster lifecycle. Download the lab guide now, and let's configure some compute. Quick reference for the 2 YAML specs you'll write in this lab. The compute instance YAML specifies type, compute instance, the VM size, and the idle shutdown timeout. 480 minutes means it shuts down after 8 hours idle. The compute cluster YAML specifies type AML compute, the same VM size, min and max instances at 0 and 4 respectively, and tier low_priority for spot pricing. Both are created with AZML compute create-file. Once you've created the cluster, you submit the test job with AZML job create-file testjob.yaml, and then watch in Azure ML Studio under Jobs to see the cluster spin up from 0 nodes. The full YAML content is in the lab guide. This slide is just the overview. See you after the lab.